everything we have talked about for the last 3.5 months. Are we almost done with the spot evaluation? Can we get started again? So I want to kind of pull everything in together and give you some perspective as how they may prepare you for a career in the gas turbine area. But that can be related to any other field, including power plant, automobile, nuclear engineering, so on and so forth. I choose this because this is what I do for my research area. So I'm going to show you all this intricate detail that we have learned for the past 3.5 months, how it may prepare you for your future work. So this is obviously a military airplane. The power plant, or the propulsion device that moves this airplane, is a propulsion engine. So it consists of fan blade at the front, which look like this. And I'm going to pass it around. So if you're an engineer working for Pratt & Whitney, which this engine is built, you're going to analyze the flow around this fan blade using what you learned from Navier-Stokes equation, which I'll describe later. And in parallel with that, your analysis is never 100% accurate because of some unknown, which is called the turbulent model. You have to do experimentation to validate your simulation. So in the laboratory, you may take a section of this fan blade and build a model like this, right? And you put it in a wind tunnel, stationary. And you make measurement using a pitot probe like we discussed, pitot-static probe to measure the velocity. And to match what you do in the laboratory versus a natural engine is dimensional analysis. It's a similitude. So what do you think you're trying to match? What do you think you're trying to match? I'll pass this around so you can see it. This is actually a model we use in our wind tunnel. Anyone? The Reynolds number. Reynolds number is something which we didn't touch on. It's called the Mach number, trying to match the velocity. Then the flow go on to the turbine section, which is something like this guy. All right, and upstream of that, you have a nozzle guide range. Nozzle guide range accelerate the flow from the combustor at like 3,000 degrees Fahrenheit to exit Mach number of supersonic. So this is a component from those engines right behind the combustor. And this is a model we built to simulate the flow around this hardware. Again, dimensional analysis. And your job is to make sure your experimentation versus your analysis can be matched and can be quote-unquote calibrated for your computational model using data from a wind tunnel to help you to take that CFD or computational fluid dynamic analysis and be able to extrapolate to other conditions that's very, very difficult to test in the actual environment. And then the company that has the best analytical tool have a leg up over the competitors. So what we have done in terms of boundary analysis is very superficial. It's almost like a joke. First and foremost, low flow is laminar in this engine. Everything is turbulent. And this so-called low pressure gradient analysis is laughable, right? Because in this kind of blading, the geometry and the flow is so complex. Nothing is laminar and nothing is zero pressure gradient. So what do we do by learning all this intricate Navier-Stokes equation and so on and so forth? Well, we want to be able to analyze the flow. This is a commercial counterpart of the engine that I just showed you. The difference is the core of the engine, which is this section, is very similar. You have a much bigger fan. This diameter is like 10 feet, twice my height, versus a very small frontal area military engine. But all the analysis and all the experimentation is similar. So as far as Navier-Stokes and computational fluid dynamics, what you are asked to do is to calculate the flow, say, within this fan stage. All right, it's typically spin at about 10,000 RPM, diameter, let's say, is 10 foot, and it's installed with a nacelle, with a cowling, all right, on the engine. So your job, if you work for Boeing or any commercial airline like Airbus, is to solve the Navier-Stokes equation, including continuity on this domain. That's what you get paid for to do. And what you do then is to set up a mesh or a grid. That itself is very challenging. How do you mesh this very complex problem? The density of the mesh, where you put them, had an influence, unfortunately, on the solution because of numerical error. Yes?
What does each cell in the grid represent?
Okay, very good. Remember our differential analysis, that's the next thing we talk about in the review. So remember Euler's equation of motion and the streamline coordinate? And then we accept a cell of, in that case, ds, dn, remember all that? And for Navier-Stokes, the past 2 weeks, we set up a cell that's dx, dy, dz. Remember all that? That's what they are. Each cell is dy, dx, dz in 3D. This is just a 2D plane cut to show you what the mesh looks like in 2D. Does that answer your question? So on each of the cell, each of those cells, what are you solving? What do you think you will solve on those cells? What equations do you think you will solve? Here's another example of those cells. Another cut to give you the complexity in 3D. What you have to do. Here's the fan blade, here's the stationary part, surface on the cowling, etc. So what do you think you will solve in that black box of computer code called maybe a Fluent or CFX, which you may use in your senior year? What are the equations that you have to solve? Continuity. And the Navier-Stokes equation, the equation that we spent so much time on the last 2 weeks, with no assumption, no laminar, compressible, viscous, everything, the whole glory, all right, with the appropriate boundary condition, such as on the solid surface of the blade, no slip, just like we did with the fat plate, same old physics, right? Do you get the sense as to how this very simple introductory course can prepare you for something like this, right? But your judgment is the physics and the basics, meaning garbage in, garbage out. I mean, yeah, it's a computer program and you can spit number out like there's no tomorrow. But if you're not careful and don't check for continuity and the basic fluid mechanics, then your solution can be garbage and you don't even know about it. And that's one feedback we constantly get back from people in industry to tell us a student nowadays don't stop and think and look at the big picture. You know, that you trust what you get from a computer simulation or from an experiment. You always have to question it. So when you solve those, which is obviously take a long time, sometimes weeks, on a very high-end computer, you can then get everything you want to know in the computational domain. Here is just a plot of the static pressure through the entire engine. This could be temperature, this could be velocity total. Everything you want to know can be provided from that simulation. But don't trust it until you make sure that the solution is physical. And that's what you'll get paid to do. And despite all this sophisticated computation, once again, they still have to do experiment for validation. Because the simulation has a lot of restrictions. All right? And the experiment can go from very simple laboratory in our lab here at Virginia Tech to flight tests, where you actually build the engine and make all the measurements. Of course, the higher compressivity, the more expensive those testing will be. But this class is here to prepare you for that type of job and career. Questions? Questions? Okay. So very briefly on the static, hydrostatic part, I think this is of interest to tie all those together. I have a brochure that's rather dated. If you ever go to Vegas, I strongly encourage you to take a day trip to visit this Hoover Dam. It's built in the 40s after President Hoover. And at the time it was built, it was one of the largest dams in the world. So we talk about hydrostatic and also fluid dynamic. This is another example of which we can kind of tie some of the things together. This picture is rather poor, but on this side is Lake Mead. This is the Hoover Dam. And I'll give you some dimension of how big it is later on. But the purpose of it is to both for recreation, you have a lake now, and for control flooding. So downstream, when you have too much water, you won't flood the bank. And the third thing is what? What can you do with the dam? Power. Absolutely. So this is what we have. At the base of the dam, there's some power station to help you generate electricity like we talk about in some of the homework. So to give you a size of how big this dam is, the brochure picture is much clearer than this. The slightly blue mark here is the size of an automobile. All right, and you can drive over the dam from Vegas to Grand Canyon, which is about 3 hours. It's right in the middle. All right, so this is how big that dam is. Those are water intake that draw water from the reservoir upstream and then feed them through plumbing, big pipe, into hydraulic turbine. How big? Before I show you that, another perspective looking from the downstream side of the dam. If you're a fisherman or fisherwoman, you know, you get good fishing on the downstream side of the dam and they release the water because all the turbulence generate a lot of activities. The fish are feeding and so forth. So looking on that side, without the water releasing through the turbine, it's very quiet. All right? And let me give you the dimension of some of the scaling that we talk about here in this perspective. So it's the same view of the dam from the downstream side, looking up at the dam and the reservoir behind. All these are released for hydraulic turbine water. And I want to draw your attention to some of the plumbing that involved. This is called a spillway, which is only used once, and that's when there's so much water. They want to divert it, not going through the turbine to prevent downstream flooding through all those plumbing. Can you read the size or diameter of those plumbing? 50 feet, 10 foot my height. All right. Even the smallest one, which is intake of the water and then feed into those bigger pipe, and then onto a smaller pipe, that's where the 4 hydraulic turbines are located. They're still sizable. This is your pipe flow, minor losses. Gravity fed, turbo machinery of hydraulic turbine. Yes?
When they were building the dam, was like the spillway, was that what they used to divert the water so they could build it?
Then for the best of my knowledge, yes, that's what they started first. Then they can have this dry area to work on. That's correct. Right. Imagine the mechanical design to make all these pieces and put them in and pouring all the concrete to get it to work. So that's fluid static, how to build a dam that won't tip. Fluid dynamic is how do you estimate all the losses through all this plumbing, and then how much power you can generate from a hydraulic turbine downstream. And they give you a tour, which I did. When you walk through the control room, you can feel the migration of the turbine running. And those turbines are huge, huge, okay? And that's enough to generate power that can power as far down to Vegas and other areas. So you don't test those turbines because you can't test it full size. It's too expensive. You build a model and you test it, significant. And then you build a full size based on your experience of the model and you hope for the best. There's no second shot. They're too expensive. So those are some limited but yet interesting application of what we have done so far. So let me end the last 5 minutes to look back at 3.5 months. What are the physical equations that we have learned that can prepare you for this type of career? So first and foremost, again, I stress and stress and stress continuity, and hopefully you will always look for that. And then the momentum equation for control volume formulation, very simple, back of envelope calculation for the first 4 weeks of the semester. You know, those are very elementary analysis, which is good for a lot of applications, but not the cutting edge, the most critical analysis like propulsion. engine. That require a lot more detail. We learned about Bernoulli equation, so I hope you all know that where it come from. Where does Bernoulli equation come from? Is it from the energy equation? No, it's from the Euler's equation. And hence, those are all those restrictions. So we went through that. Hopefully you remember how to get to that point. Then, from there, we look at pipe flow. First, we have this added equation of energy, which is the first law, written in a very peculiar form, which almost looks like Bernoulli, but it's not. In that I have now capability to account for shaft work through a pump or a turbine, and then I can also account for all the losses due to friction, head loss. And this equation is the new added physics. So if I want you to remember only a few equations at the end of this semester, and for simplicity, let's just call it 5 equations. That will prepare you for your future career in any field relating to thermal fluid science, like gas turbine, nuclear engineering, power plant. Can you tell me what those 5 equations are? Continuity, momentum, Bernoulli. Very good. Those are what we cover in this class. Anything else? No, Navier-Stokes is one of momentum equation, just a cousin. So I got 3. Momentum, continuity, momentum, Bernoulli, very good. Energy, first law, which is what we're dealing with right now. First law, okay? Which you see a lot more in different form in thermodynamics, which we didn't cover. First law. What about the 5th one? It's also from your thermodynamics, and it's something that you really hate.
Second law?
Second law. To predict the losses in this kind of device, I need second law. 5 physical equations will guide you for the rest of your career. Coupled with that, this is not easy. You will have property of the fluid, steam table, for example. And if you got air, you can possibly use ideal gas. So you have 5 physical equations and 1 what I call in the thermodynamic equation of state. That will serve you well for any job you will encounter for your entire career. Okay? Do you see the big picture? I mean, a year from now, if I have you again and ask you that, I bet you most of you don't remember. All right? So, what else? Last 2 minutes. We talk about pieces of similitude, dimensional analysis, matching all the pi term, Reynolds number, etc. Here's the differential analysis that someone asked me just 5 minutes ago. This is the building block of how we get the Navier-Stokes equation. You are capable of doing that now. We've done it for continuity in 3D. And then from those differential analysis, we developed the Euler's equation as, just an appetizer. But you can go much further and much more sophisticated than that. Towards the end, we talk about external flow, drag coefficient, lift coefficient, just very lot table lookup. Boundary thickness, delta star, and theta are things that we didn't cover, so you won't have to be responsible for. But the key takeaway for viscous flow is separation. So what is the key takeaway for separation? Adverse pressure gradient. Keep it simple, bare bone. If you can remember that, that will serve you well. Any devices where the exit pressure is higher than the inlet, not a compressor, not a diffuser, look for trouble. And from those Navier-Stokes and simplifying analysis we just saw today, how Bassius were able to simplify the Navier-Stokes equation and obtain some pretty nice closed form solution. But that's more exception than the norm. Primarily, you have to rely on computer simulation. Okay? Good luck.